Hi guys, today we're going to be looking at heme synthesis, a very important topic both from NEET as well as competitive exam point of view. So let's get right into it. One common question we see is what are the precursors of heme? So it comes from glycine and succinyl-CoA. Glycine, as you might know, is the simplest amino acid. It has amino, acid, and a carbon with two hydrogens. Simple guy. Then we have succinyl-CoA. Succinyl-CoA, if you remember, comes from the TCA cycle or the tricarboxylic acid cycle or the Krebs cycle. It's one of the intermediates, right? Now, what do? We take this glycine, take this succinyl-CoA, take an enzyme called ALA synthase. Let's see what is ALA in a bit. And let's not forget PLP. PLP is the coenzyme here. What is PLP? Pyridoxal phosphate. And what's that? It's nothing but the coenzyme form of vitamin B6. So, one of the vitamins you need for the synthesis of heme or hemoglobin for that matter is B6. Take out a CoAsh. Now, it's basically coenzyme A along with a sulfur hydryl group, but we like calling it CoAsh because it has a nice ring to it. Take out one CoA and one hydrogen from the glycine, put the rest of it together. What do you get? You get alpha amino beta keto adipic acid. Now, there's no need to by heart this. Let's make it simple. If you remember your 11th, 12th grade organic chemistry, how does nomenclature work? You start from carboxylic acid. We have two carboxylic acids here. Start from the more important carboxylic acid. So, whoops, my bad. Just a second. Yep. So, we start numbering from this. So, this is our first carbon. And then we have, or some people call it the hero carbon, right? Then you have alpha, beta, gamma, delta, and so on. So the alpha carbon has an amino, the beta carbon has a keto, and this skeletal structure gives us adipic acid. So we have alpha amino, beta keto, adipic acid. You don't have to learn the structures, but the structures give you an insight about the pathway and make it simpler, right? So we have alpha amino, beta keto, adipic acid. Next, same enzyme ALA synthase, same coenzyme PLP. This time remove a CO2. Where is the CO2 removed? Where are we removing it from? We're removing the main CO2. So what do we have here? Now if we start numbering this will be our hero carbon, alpha, beta, gamma, delta. So what we have here is called delta amino levulinic acid, or in other words, amino levulinic acid, or ALA. So we're done with the first two steps. Next, what do? They're taking two ALAs and removing water. So without even looking at it, I can tell that the enzyme is probably a dehydratase, right? So take two ALAs, remove water, remove two water. And next you get porphobilinogen. So how did we go from this to this? We're removing two waters and the rest of it is binding in the form of a pyrrole ring, right? And if you remember, heme is actually a tetrapyrrole or pyrrole, however you want to pronounce it. So this is where we get each pyrrole ring from. And this ring along with the rest of it, don't worry about the other attachments to the ring, but just know that this is called porphobilinogen, right? Or PBG. Some people call this step a PBG synthase step, but personally I don't want to, because it's not a synthase in the strictest sense. You are removing water. Now 4 of these PBGs, so imagine another ring like this and another one, right? 4 PBGs, this nitrogen is removed, nitrogen in the sense ammonia is removed. 4 PBGs, 4 ammonia removed, and the enzyme here is deaminase. Who would have thought? It's very basic and intuitive and logical. So when you put it together, you get uroporphyrinogen 3. Now this, don't worry about this 1, 2, 3. Just know that in humans, all the heme has 3, right? Uroporphyrinogen 3. And to this UPG3 is attached an acetyl group, a propional group. Acetyl, propional. Acetyl, propional, propional, acetyl. So it's AP, 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 and the last two is PA. Right, so why does this matter? Sometimes if you need full marks, the examiners will expect you to write this as well. So yeah, you have 4 acetyl groups, 4 propional groups arranged in this format. Please note, this is not the structure itself. This is just a representation of the structure so that we can understand it better. Moving on, from UPG3, we remove 4 CO2. Right, so all the acetyl has CO2, if you remember. It's like, acetic acid. Think acetic acid. All the acetyls are converted into methyl. 4 CO2 is removed, and we have coproporphyrinogen 3. And I can already tell this is probably a decarboxylase. Yes, UPG decarboxylase. Next, like I said, since the acetyls are converted into methyl, now we have MP, 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 and PM. So only the last two are, switched. Next, this step is pretty important. Oh, before I forget, this PBG PBG deaminase, which means step number 3 in this, is also called UPG synthase. So this actually happens in 2 steps, right? First step is UPG synthase, and second step you need something known as co-synthase. So you need 2 enzymes, UPG synthase, UPG co-synthase. Some people call UPG synthase as PBG deaminase. So let's make it very simple. From PBG to UPG3. How do we go? We go in 2 steps. You can just write it like this. The first step requires PBG deaminase. In other words, UPG synthase. And the subsequent step requires UPG co-synthase. So I hope I didn't confuse you. Right, so where were we? We are in coproporphyrinogen 3. Next, we need NADP. Please note, it's not NADH, it's not NADPH. NADP to NADPH. So, is this an oxidation or a reduction? Remember, NADP came alone. It just came as NADP. But it's leaving with hydrogen. So, NADP is getting reduced, which means this is getting oxidized. So it's an oxidation that's happening, and in the process all your propional is converted into vinyl. So all the P's in your MP becomes V now. MV, MV. Not all the V's, only 2 of the V's become V, 2 of the P's become V, and the rest of it remains as it is. So we have MV, MV, MP, PM. Okay? And this enzyme is coproporphyrinogen oxidase, which we already knew because we knew that this is an oxidation step. In the process, an O2 gets converted to CO2. Next, what do we get? Protoporphyrinogen. We're almost there, you guys. Protoporphyrinogen, 4 hydrogens are leaving. Again, if hydrogen is leaving, it's an oxidation step. This is all your basics from 11th and 12th grade. So it has to be strong, but even if it's not, it's okay. We'll get there. What happens when you oxidize protoporphyrinogen? Gen is always precursor, gen. From some gen, you get something. So from protoporphyrinogen, you're getting protoporphyrin 3. Again, remember, this 3 which came in UPG continues till here, okay? Now it's protoporphyrin 3. And protoporphyrin combines with heme ion, or basically ferrous ion. What do you think the enzyme is? Obviously heme synthase or ferrochelatase, because you're gonna chelate this ion and finally form heme, which looks something like this. So what was the last alteration we did to the groups? We made it MV, MV, MP, PM. You have that. You have your 4 pyrrole rings, and you have the heme ion or the ferrous ion in the center. That's it. It's as easy as that. I think I'll tell the regulation also in the same video. Regulation is very easy. This first ALA synthase wala step, and again for the exam you can directly write glycine plus succinyl CoA gives ALA. You don't have to write the adipic acid step, but stuff like that gives you the extra edge. Heme is repressing. What is repression? It's basically a type of enzyme inhibition at the gene level, right? Which means, let's say you have so much of heme everywhere. All these hemes will go and inhibit ALA synthase. So they'll be like, stop making more heme. We already have enough. What else is inhibited? Lead inhibits ALA synthase. Lead. Hematin inhibits ALA synthase by allosteric regulation. I'll make a different video on allosteric regulation. And glucose also inhibits this. What is the application of this? In lead poisoning, your heme synthesis gets inhibited, right? So you have defective heme, defective hemoglobin, and anemia. So you have microcytic hypochromic anemia in lead poisoning because of this, right? And glucose is inhibiting ALA synthase. उससे हमें क्या लेना देना? If you have enough glucose, or in other words you have enough carbohydrate rich food, your heme synthesis is inhibited, and this comes to use in porphyrias. One of the treatment for porphyria is just glucose or dextrose. So pretty cool. Then our ALA dehydratase step is also inhibited by lead. What else? Yeah, the final step, the ferrochelatase or the heme synthase wala step, is also inhibited by lead. In other words, lead interferes with heme synthesis at 3 steps: your ALA synthase step, ALA dehydratase step, and ferrochelatase. So that's it for today. I hope this was useful.